It is the defining tension in AI right now. We, as users, we demand this instant response from large language models.
Right.
We want super strict performance, that time to first token or TTFT, and then really tight latency between tokens.
Absolutely. But serving these models, I mean, it's not just expensive, it's crippling for infrastructure.
And that's where our sources point to this core inefficiency that's driving all these costs. The way we typically handle scaling, static provisioning, or even just scaling the whole model, it treats the LLM like one giant solid block, a monolith.
It does. And if you provision for peak demand, that P95 traffic level, you're just reserving huge amounts of power that, well, it just sits there.
So it's just idle most of the time.
A lot of the time. The analysis we looked at shows that even for normal text workloads, you might only hit 50% of utilization.
Okay, 50% is already pretty bad.
It is, but what really stood out was the data on multimodal workloads. There, utilization can drop to a shocking 39%.
Wow, okay, wait. That's a huge gap. An 11-point drop just for multimodal. Why? What's so different there that causes that massive dip in efficiency?
It really comes down to the model's architecture. Multimodal models, they have these extremely large and specialized layers for handling images or audio.
Like a projection layer or something.
Exactly. And those operators have totally different compute and memory profiles than the normal text-based attention blocks.
So when you scale the monolith,
So you have to scale the entire thing to handle the peak demand of that one specialized and, frankly, infrequently used part. The rest of the model is just waiting.
that makes perfect sense. So that's our mission for this deep dive. We are going to completely reject that monolithic view.
Right.
We're going to unpack the LLM's internal structure and show why scaling at the level of the operator, the individual bit of math, is just. It's the superior way to do it. And the findings, they're really compelling.
They are. We're talking about preserving those strict SLOs, but with far greater efficiency.
To get there, though, we have to start with the model's anatomy. We have to stop treating it like a black box.
Exactly. Internally, an LLM isn't a monolith at all. It's a directed acyclic graphidag of all these connected operators. You have your attention blocks, your linear transformations, normalization layers.
Right.
Those are the real fundamental units of work.
So what are the actual consequences of model-level scaling completely ignoring this internal map?
There are two big ones that just kill efficiency. First, it is way too coarse-grained.
Meaning you scale everything at once.
Everything. The heaviest attention layer and the lightest normalization step, they all get scaled up uniformly. So if a really long prompt only stresses the attention operator.
You're still wasting cycles in memory replicating all the other parts that were never the bottleneck.
You got it. And the second consequence is just speed, or I should say the lack of it.
Right, elasticity.
Right.
LLM traffic is so bursty.
It's incredibly dynamic. But our sources show that loading a full replica of a big model, say 70 billion parameters, onto a new GPU, that can take 10 seconds or more.
10 seconds is an eternity in an API call. That's the user closing the tab because the time to first token SLO was just blown out of the water.
Precisely. And that's why the operator becomes the right unit to scale. It enables fast elasticity. These operators are so diverse in their needs, by scaling only the component you need, maybe just a few linear layers, you drop that scaling latency from tens of seconds down to, sub-second.
That kind of surgical adaptation seems like the only way to manage costs while keeping users happy.
It is.
Okay, so let's really unpack this heterogeneity because this feels like the absolute core of the idea. Let's start with compute. How do these different operators behave, especially during that initial prefill stage?
This is where the attention operators are the clear bottleneck. Their complexity is quadratic with sequence length. That's O of L squared D.
So every new token in the prompt has to look back at every other token before it?
Exactly, and that pressure just ramps up dramatically as the prompts get longer. Most of your GPU compute during prefill is spent right there.
Okay, so how much less sensitive are the other components then?
Oh, significantly. Things like feed-forward layers or normalization, they mostly scale linearly, so O of LD. Some are even flat. But what's really fascinating here is that the bottleneck isn't static. It's dynamic.
It moves.
It moves. Attention might be the problem at 4,000 tokens, but at shorter lengths, maybe it's a different linear transformation. So a good scaling system can't just react to what's slow right now. It has to predict how that constraint is going to shift.
Okay, so compute is super sensitive to length, but memory is the other half of this puzzle. How does that map onto the operators? I mean, we used to think attention was the memory hog too, right? Growing quadratic.
That was the old thinking, yeah. But new tech, like flash attention, has completely changed the memory game.
Right.
The memory complexity for attention is now basically linear with sequence length O of L.
Yeah.
So the crucial insight here for disaggregation is the uncorrelation between an operator's compute and its memory needs.
Uncorrelation, meaning they aren't all demanding the same thing. So what's the worst case scenario for monolithic scaling if they're uncorrelated?
The guarantee of waste. It's guaranteed. Take a normalization operator. It can be super memory intensive because it's handling these huge intermediate data structures, but it's computationally very light.
And on the flip side,
You have things like reshape or caching operations. They can be compute heavy but need very little memory.
and attention is kind of in the middle, needing both.
Right. So if you scale the whole model uniformly, you are guaranteed to be either over-provisioning memory for a compute bottleneck or over-provisioning compute for a memory bottleneck. There's no way to win.
Okay, that makes sense. So there's one more piece here, queuing sensitivity. How these operators react when you just throw more traffic, more requests per second at them.
And they hit a wall non-linearly.
Mm.
The latency shoots up way faster than you expect,
So the most demanding operators are the most sensitive to queues.
by far.
Yeah.
That quadratic attention layer with a long prompt or the biggest linear operators in a mixture of experts model, they need the sharpest increase in replicas to keep those queuing delays from spiraling out of control. The sources are clear on this. You have to combine compute profiling with queuing models to be efficient.
This brings us to the most practical part of our deep dive, the real-world results. We have the theory, but what happens when you actually implement this using real deployment traces from places like Azure and Mooncake? I mean, where are the savings actually maximized?
The gains are substantial, but, and this is critical, they really depend on the workload, specifically sequence length and the arrival rate, or QPS.
Right, let's start with sequence length.
All right, so we see GPU savings peak at around 30 to 40%, but they peak at moderate sequence length, say, around 4,000 tokens.
Wait, that's interesting. Why do the savings peak there? Why not at the absolute longest context, like 32,000 tokens? Wouldn't the problem be worse there?
That's a fantastic question, and it gets right to the heart of that dynamic bottleneck we talked about. At moderate lengths, like 4K, that quadratic complexity of attention really starts to dominate everything else. It creates this very specific, very local bottleneck.
Ah, perfect target for surgical operator level scaling.
The perfect target. But at extreme lengths, the entire GPU just becomes saturated. All the streaming multiprocessors are running flat out. At that point, the bottleneck isn't one operator anymore, it's just the raw hardware limit.
I see. But I did notice in the data, the memory savings trend seems to defy that logic. It just keeps going up and up.
It does. Memory's a whole different beast. The savings there are dramatic. They grow steadily, and they surpass 60% at really long sequences, like 32K or 64K tokens.
Why?
Because even linear memory growth at that scale for things like the KV cache is just enormous.
Yeah.
Operator-level scaling saves so much because you're not replicating the massive model weights and all that intermediate data for operators that weren't the bottleneck. The memory efficiency gains are huge.
Okay, what about the arrival rate, the QPS? Where do we see the most benefit there?
We see the GPU savings peaking near 30% at what you call moderate to high QPS, maybe around 40 requests per second.
The sweet spot.
It's the sweet spot where this kind of scaling is really good at consolidating workloads and avoiding over-provisioning when you get those typical traffic bursts. If the QPS is super low, well, one instance can handle it anyway, so there's not much to gain.
And if it's pathologically high, you run into that same hardware saturation problem.
Exactly.
Okay, here's what I thought was the most critical disaggregation insight. Comparing prefill versus decode. The sources found one of these phases offers way more optimization potential.
That's right. The prefill stage offers something like 2 to 3 times greater resource savings than the decode stage. We saw prefill hitting up to 35% GPU savings in real traces. Decode savings were often stuck below 15%.
Why such a massive difference between processing the initial prompt and then generating the new tokens? This has to tie back to those SLOs.
It does, directly. Prefill is compute intensive, and it's inherently bursty. You get a long prompt, you process it, and you're done. That makes it a perfect target for this kind of elastic scaling.
So you can spin up resources and then spin them down right away.
Instantly. Decode, on the other hand, is usually memory bound. It's limited by the size of the KV cache. And it operates under much, much tighter latency budgets because of that time between tokens SLO.
Right, the TBT, you can't have a long pause between each word.
You can't. And that tight constraint just limits your flexibility. You can't be as aggressive with scaling because you have to keep resources warm and ready to go.
Finally, how does this all change with just the raw size of the model? Does scaling a small model benefit as much as a truly massive one?
The benefits are definitely amplified by scale, significantly. For the smallest models they looked at, like a half-billion parameter model, the savings were pretty modest, below 15%.
But for the big ones,
When they analyzed the largest model, a 72 billion parameter one, the energy and memory savings peaked near 50%. As models get bigger, their internal complexity and sort of resource fragmentation just grows geometrically. The monolithic approach becomes exponentially more wasteful.
so the bigger the model, the more you need this operator-level approach to hit your SLOs without going broke.
That's the takeaway.
This deep dive has really changed how we should be looking at LLM infrastructure. We've shown that moving from that coarse monolithic model level to a fine-grained operator-centric architecture, it provides a precision that can fundamentally change a provider's cost-to-serve ratio.
The core message for you, the listener, is that efficiency demands granularity. It really does. Understanding the heterogeneous nature of that computational graph, how one operator is quadratically sensitive to compute while another is linearly sensitive to memory, that is the absolute cue. It's how you balance what the user wants with what the provider needs.
So what does this all mean for the future of LLM architecture? We know this operator-level autoscaling works great, especially with things like pre-filled decode disaggregation. But there's this other push in the industry, right? This race for ultra-low latency, which is leading to research into mega-kernel fusion.
Fusing operators together for speed.
Exactly, where you combine many operators into one single massive kernel to get maximum speed. So my question is, if the industry moves entirely in that direction, toward a monolithic fused architecture that prioritizes raw speed, does that kill the opportunity for this kind of fine-grained optimization we've been talking about? Or will the brutal, persistent need for efficiency always demand this level of granularity, forcing a hard trade-off between monolithic speed and fine-grained elasticity? Something for you to chew on until our next deep dive.